and thank you for holding out that late with us. So today we are going to discuss a little bit about service mesh and how to handle that if you have more than a single Kubernetes cluster. But let's first introduce ourselves. I'm David Meder-Marouelli, and I'm with One Mail and Media since 2015, so like 7 years now. That's sort of my latest position in the IT industry. My career goes a bit further back than that. And over time, I evolved into an expert of continuous integration and continuous delivery, and that essentially brought me to my current position, which is being the lead architect for our delivery platform. I'll talk about that briefly. And live, with a remote connection, we do have Stephan Fudeus, who is one of our subject matter experts. He has a similar career. He's 15 years with about 15 years with One. He's in mail and media since 2017, and he's our expert for container technologies, and consequently, he's our tech lead and product owner for the Kubernetes platform within our delivery platform. So, delivery platform, I said that already twice, and let's have a quick look at what we mean when we say delivery platform. Okay, that should have had an animation. Doesn't work, doesn't matter. So you see everything at once. That's fine as well. Yeah, so delivery platform, what does that mean? Of course, we did develop a vision. Come on, guys. On the right-hand side, there's lots of seats free, just pass through. So we do have a vision, and the vision is that we provide a platform to our developers and engineers that provides all the services and processes that you need to develop and run your application. And consequently, our engineers can fully focus on the business logic of the application. So that enables us to use and leverage cloud-native patterns easily. And, well, as I'm the lead architect for a large platform, and architects love simple pictures, that's a simple picture how we translated that into a technical platform. So the delivery platform really starts with the first line of code, or even before that, with code templates for new applications, which we provide to our developers. It supports with the code handling, like with the Git repository and stuff like that. And then we also have the continuous integration, continuous delivery part. So we automatically, in the platform, can build the applications into executables and deployables. And of course, the continuous delivery part is making sure that we can stage that through the various environments to reach production in the end. So that's propagating the artifacts through development, QA environments, and through production. And production ultimately means we do have deployments into hosts, quite classically. That's not what this conference is about. But we do also have Kubernetes. And, well, little surprisingly, Kubernetes has evolved into the platform for our runtime environment. And that's a nice thing, because that conforms very well with our vision, because Kubernetes automates away lots and lots of administration processes, so the admins get really relieved of a lot of toil and can focus on the application and the business logic, which is a real nice thing. And one of the things that Kubernetes nicely implements as well is, of course, networking. But the vanilla Kubernetes networking stuff, including many of the overlay networks, is essentially providing networks in a way that feels quite classical, like providing IPs, providing virtual interfaces, stuff like that. But if you sort of absorb the cloud-native paradigm, your applications will need more in terms of networking and higher-level abstraction networking functions. And that would also fit nicely with the vision, relieving engineers from the toil and the things that are not business logic. So service meshes to the rescue. And here's an advertising sentence from Istio from a couple of years ago. So Istio promises us that it addresses all the challenges that developers and operators have with distributed microservice architectures. Yes, we have that. We are building, we are migrating existing stuff. So that sounds really, really exciting for us. So let's see if we can fit in a service mesh into the requirements of our platform. So the two top features that we were able or can sell to our developers is you don't need to take care of that mutual or TLS stuff at all, because Istio can take care of that. And it's a constant pain equipping every application with a suitable, secure TLS library and handling the certificates on top of that. And of course, metrics and tracing come for free in service meshes, and that's a real nice thing too in terms of instrumentation. So that's a quick view of our clusters, and you see we do have Kubernetes in the center. We do have servers around which run classical applications. So that immediately leads to the first requirement. We do need to integrate host-based applications with Kubernetes applications, ideally in the service mesh. So service mesh expansion is one of the very important requirements here. And that's not all. Let's look further. We do have more than one cluster. Okay, title says it all for that talk. We do have more than one cluster. We do have a segmentation into front-end and back-end, but we do also have multiple data centers. And of course, the applications need to talk across the cluster boundaries. So front-end needs to talk to back-end. But we also want to be able to do geo-failovers between the data centers. So these clusters need to be able to talk to each other as well. So multi-cluster operations is a real important thing. And then, of course, service meshes bring lots of other benefits, like traffic management, routing stuff, policy management. So all that nice, smaller and bigger features that make a service mesh worthwhile. So what does the lead architect say here? That's really cool. That's so cool that obviously everybody wants to have that immediately. So that's the aspiration anyway. And as a platform architect, I say, yeah, okay, let's define 4 simple steps. First, rollout Istio on the clusters. Second, provide Puppet-based installation methods for the hosts. Third, have the users adapt their already highly standardized rollout manifest a little bit and re-roll their applications and be happy ever after. And at that point, it's certainly time to transfer that task to a real Kubernetes expert. Fortunately, I do have one, and we do have Stephan around here as well. So he'll talk us through how we get that actually done.
Yeah, so I will take over. Welcome from my side as well. Sorry if I can't be on stage. I would have preferred to do so, but I need to attend urgent family business tomorrow morning, early in the morning, and that's just not sufficient time to drive back home. So I hope you can hear me well. Let's look into our first issue with that aspiration, because it's not as easy as people would try to sell you the story as you have expected, especially when we go into DNS. If you had listened to Michael Friedrich's talk just in the slot before, he had one slide regarding it's always DNS. And of course, DNS is a crucial thing in service meshes as well. So essential, no multi-cluster or mesh expansion is possible without DNS, because how do services and workloads talk to each other? They discover themselves via DNS. And yes, of course, Kubernetes has DNS inside, but usually host-based applications living outside of Kubernetes don't have native access to the Kubernetes DNS. So they don't see the stuff within Kubernetes. And then Kubernetes workloads, they need insight into other clusters if we consider multi-cluster. Usually they see their own stuff. They see the standard DNS outside of Kubernetes, but the internal DNS of other Kubernetes clusters is usually not visible. And then, of course, names which are invisible in Kubernetes are invisible to cluster workloads. So Kubernetes lives off services, and DNS is populated based on services, but Istio service entries, they by default are not part of DNS resolution. And the last important thing is Istio originally becomes only active after DNS. So it intercepts IP traffic. But how do you get to starting your traffic, initiating your connection? You need to have a proper DNS resolution, and Istio must be then able to intercept that IP address. So cluster internally, it's just sufficient to enrich existing services, but external services must somehow be made available into Istio. So originally there was the Istio Core DNS plugin. So it's really a plugin into Kubernetes Core DNS. And this plugin handles service entries. Istio defined a .global top-level domain and handled traffic for .global specifically. If you create a service entry with a .global host entry, this was picked up by the Core DNS plugin and made available with an 240.something IP address within Kubernetes DNS. But this is a thing which was just available in cluster. Everybody outside of the cluster didn't see that if you did not expose your Kubernetes DNS service to the outside world, which is doable, but not the standard. This Core DNS plugin was available in Docker Hub, but as you can see in the screenshot, there only have been 2 releases. And even when this was still the way to go for multi-cluster stuff, it wasn't properly maintained. It was years old, the last release. And for multi-cluster, this worked well for remote services. So if there's this thing which is just outside of your mesh, you could integrate that with a service entry into your cluster. Failover was a bit problematic because local entries would always win and you wouldn't see the external world. For mesh expansion and the outbound side, so if you have a workload in Kubernetes reaching out to an expansion service outside Kubernetes, this worked well as well. You just have the .global. But for inbound, it didn't work. You would have to expose your Kubernetes DNS service to make that usable. And then it could work. So it worked half. If we then the next iteration to that, because it had shortcomings as we see, and the next iteration in Istio was DNS interception. So not only the payload traffic is intercepted, but already the DNS requests. And this was introduced with Istio 1.8, so in November 2020, kind of late after the 1.0 release of Istio. And 1.8 deprecated this .global top-level domain and the full Core DNS plugin, which hadn't been updated for 2 years anyway. So that last image was from March 2019. And DNS proxying was introduced, which is an optional feature. And this defines that even DNS requests, so everything on port 53, is intercepted by default from your sidecar proxy and handled by that one and resolved via a kind of caching DNS proxy. I linked the documentation link for Istio here on the slide. The problem with that is this was still not enabled by default for pods. Just if you do mesh expansion for hosts, there it was enabled by default. And you might not want to enable that for all pods by default because it might have side effects which you should evaluate properly before. There might be workloads which have high requirements regarding answer times of DNS, response times, and you really should look into how that DNS proxy is behaving and how it adheres to TTL definitions for DNS. So was this now the final solution with Istio 1.8? Inbound expansion worked very well with that because you now had DNS interception and saw the full Kubernetes DNS. Everything fine, not restricted to .global, all good. Outbound expansion was a problem, and we will see in a second. And multi-cluster was still only possible if you exposed your, if you created additional service objects within Kubernetes, which you wouldn't need for the service to make it work. You just had to create service entries to make them available in DNS so that they are resolvable. Then you could do multi-cluster with 1.8. And now let's do a short excursion. How does Istio interception work in general? So it uses IP tables or newer NF tables. And there are two options to configure your network interception. The original version was you have privileged init containers, which use netadmin capabilities of the Linux kernel. But that meant if you use pod security policies, you had to enable for these namespaces where you wanted to use Istio, you have to provide that capabilities. You need to allow pods with that capabilities. And you couldn't restrict it on Istio. So that your users, your tenants, could just use netadmin pods then as well. And that's not a nice thing for most platform operators. And of course, Istio had a different solution to that, which is Istio Cni. It existed since Istio 1.11 in an alpha version from March 2019. But the problem with Istio Cni is this DNS proxying was unfortunately not implemented for Istio Cni. You had to wait for the next Istio version. David, next slide, please. I think my 1.11 from the slide before was wrong. The DNS interception was implemented in 1.11 in August 2021, and it went to the beta version then. So only then, 1.11, this looked good. So is that a solution now for our DNS problems? Inbound expansion was already well with 1.8 and still good with 1.11. Outbound expansion now works because you can enable DNS interception for pods as well. And multi-cluster, yeah, that's possible as well because all your pods have the full DNS influence, and even service entries within Istio are automatically visible for Istio-enabled pods. The only remaining question mark here is, what about performance? What about workloads which do have high demand on DNS resolution? This is something which needs to be tested. We are a mail provider, so we do care. We do a lot of DNS resolution when we put the relevant workloads into our Kubernetes clusters. Okay. But enough about DNS. Of course, if it's not DNS, it would be BGP. But let's not talk about BGP, but let's talk about control plane scalability first. As you know, Istio has its own dedicated control plane. It used to be a microservice architecture with a bunch of components, and eventually they put that together into one monolithical Istio D instance again, because all the components were updated all at the same point in time anyway. And this control plane just holds all the data, which is consumed then by the sidecar proxies. And there are multiple models how you can deploy your control plane in Kubernetes. You can just deploy your control plane isolatedly into any of your Kubernetes clusters. They don't know anything about each other. They are just there, and you need to configure everything outside them with service entries. That's an easy thing. You can just do that, but it has some consequences. But of course, it's the most consistent and isolated approach. The second option is you can make the Istio control plane aware of other clusters. And then the Istio control plane talks to other Kubernetes APIs and gathers the information from there and makes it available locally. Of course, by that, you gather a bunch of knowledge about services and other clusters, and of course can auto-configure several things within the Istio control plane. The third option is you even can say, hey, I don't want to have a local control plane within my Kubernetes cluster. I externalize that fully. So like in an infrastructure cluster, you deploy one large Istio control plane over there, which has the knowledge of all your Kubernetes clusters. It's a bit easier to maintain, less moving parts, but of course it's more centralistic. So let's talk about or look into how does that scale. If you have, of course, Istio D itself can scale. You can have multiple replicas of your Istio D instances within a single cluster. And that scales well with the amount of sidecar proxies you deploy in your clusters. So if you have more applications, more workloads in the clusters, more replicas of those workloads, they can talk to Istio D. And if it's too much for Istio D, it will just scale horizontally and get all the predefined data for the sidecars. But the Istio instances somehow need to get their data model, and they get that from the Kubernetes API servers. Each instance of the Istio needs to get this information from the API servers. So the more Istio you have, the more load on your Kubernetes API servers to gather that information. And the work to be done there, so the CPU time and the memory needs, that just goes up with the amount of Istio instances. And if you even let the Istio talk to multiple Kubernetes API servers from multiple clusters, that of course just raises the amount of resources to be processed, and it increases the load on the Kubernetes API servers. So there's a big to-do. You need to check if your Kubernetes API servers and your Istio can scale with the amount of workload you enable for Istio. Especially if you have large applications, which a high amount of replicas, like a typical thing for us is that applications go up to 350 pods on a 300 node cluster. And you see in that sizes of clusters, there's quite some traffic to be handled from Istio. So let's look a bit into multi-cluster failover and ideally keeping data local. So looking into locality distribution. There are usually two separate use cases for using multi-cluster. The one thing is you just want to make things available which are not running locally. There's just something which is in a remote cluster and you want to contact that. That's use case number one. And the use case number, that's kind of from what David showed from our topologies. That's like talking from a front-end cluster to a back-end cluster. Usually they have separate kinds of services. Use case number two is you want to have failover between services. So you have a service running locally and in a remote cluster for geo-redundancy, for example, and you want to make that available. And these are conceptually two completely different things. With a shared control plane, that's just supposed to work out of the box. So if every Kubernetes control plane knows every other cluster and what's deployed inside, all the Istio have all the information they need. They know all the endpoints. They know all the gateways. They know where to reach a certain endpoint. Failover in Istio there is possible based on regions and zones and so-called subzones. Regions and zones are just the standard Kubernetes nomenclature, and Istio defined an additional subzone to use. What you need to do to make use of that, for all of your workloads, you need to define outlier detection, because only the outlier detection will help you identifying if an endpoint is healthy and if traffic should still be sent there, or if it needs to fail over to a different endpoint, a different region, or different failover definition. So it goes into region, zone, and subzone. There is even locality-weighted load balancing. So you can, by default, not just failover, but you can distribute your traffic across different locations. But usually, of course, you want to work as local as possible, as long as your local workload is still healthy. If it goes down, only then you intend to failover, but ideally then a bit gradually. If you only have 2 local endpoints left from originally 300, maybe it's not good to have 100% of load onto those 2 endpoints. With isolated clusters, so not with a shared control plane, and if you manually maintain your service entries to make remote stuff visible, of course, that looks a bit different, because then you need to do that on your own. As said, you need to define service entries on your own. And even local traffic must be explicitly mentioned. So it's one of the items in the endpoints listing of a service entry. In this example I show here, you see the first endpoint in line 14. There's some servers in namespace 2 in service cluster local. That's a local endpoint in region 1, zone 1. The locality is defined in line 17 for that endpoint. And you want to point it to a remote cluster as well. And that needs to be done through a ingress gateway, because usually, and in our cases as well, of course, the pod network of a remote cluster is not directly routable. You need to go through exposed IPs, which are the ingress gateways. And so here, there's a definition in region 2, zone 1, there is an ingress gateway, and you can send traffic there as a failover possibility. The problem with that is that remote side, it's just defined by that entry in line 18. Has a single health state, so you don't know anything about the amount of endpoints behind that definition, and how many of them are healthy. You would just notice if nothing works anymore at all. So as you see, that all that stuff is not trivial. And there are helpers, and some of them already exist since a while. So there's Admiral, already originally created by Intuit. And Admiral helps connecting multiple clusters and transporting information from one cluster to another. It has a CRD definition, the global traffic policy, and with that you can define which services shall communicate with which other services in which clusters. And then there's a newer thing, which is Kubernetes multi-cluster services. So multi-cluster is even moving on to Kubernetes into the core, or at least into the core project. It's defined in CAP 1645. It has already experimental support in Istio 1.11. There are two additional CRDs, the service export and the service import, and there's a bunch of additional stuff as well. But as you would see from the naming, you just export a service with a service export CRD in a source cluster, and in other clusters you can just import that service, and by that you define that data about that service should be visible. In fact, there is even a on-demand talk here in ContainerDays, multi-cluster Kubernetes today and tomorrow from Laura Lawrence. I would urge you to, if you are interested in that topic, have a look at that on-demand talk as well. So let's go to migration challenges. So away from the issues, but it's an additional problematic part of introducing multi-cluster Istio. If you use Istio in a decentralized way, and that's from the maintenance perspective, so you have a platform team which is managing your Istio control plane and your Kubernetes control plane, but you don't want to manage all the Istio service relationships in that central platform team. That's supposed to be in the hands of the application teams. But if you do that, somebody needs to define those remote workloads and service entries. Who's doing that? And so that's especially the non-mesh stuff, host-based workloads, and there's workloads in remote clusters. And you need to take care of duplicates, because Istio doesn't really like it if there are duplicate definitions, even if they are semantically identical. So you need to somehow get rid of that duplicates. And there's one workaround mechanism in service entries, which is the export to function, where you can reduce the scope, the visibility of a service entry asset. And with export to dot, you can restrict visibility to the local namespace. And if your tenants are isolated across namespaces, then they don't affect the others anymore as well. You can export your services to other namespaces if you explicitly wish so. Then you can just name your namespaces in the list of these export to array. And yeah, non-Kubernetes stuff. By default, everything outside of the mesh is invisible for security reasons. And if it's invisible, it's unreachable from the mesh. You need to define service entries for them. And this means all your developers which are deploying their workloads, their applications, they need to have the general awareness that they need to define whom they want to talk to. And that means this stuff needs to be defined in deployment pipelines, and you have some amount of redundancy in your configuration management. Or your configuration management must be centralized in a way that you can generate all necessary artifacts. That means application configurations and service mesh definitions out of that central information in your configuration management. And the last thing,
we're running out of time.
Okay, then yeah, let's skip that.
Okay. So you see, there's lots of other things to discuss. Let me quickly shed a little bit of light on usability issues. Obviously, there are various ways of making your users adopt a technology like that. I'll skip that quickly, but the core of that is you need to provide real good automation, and you need to provide generators for all that manifested Istios and potentially other service meshes need. So by automating and centralizing that, you're making sure that you get consistent default values, you avoid any kind of conflicts, and obviously everything that's generated is avoiding toil for the admins. But you need to be careful to balance the level of abstraction against the feature completeness, against the maintenance that you need to put into the automation. And essentially, our default is to provide 3 levels of abstraction. The basic level that has very few parameters to tune, just essentially switching things on, and it should run for default application that covers usually 60 to 80% of the applications. We do have an advanced level for the sort of common corner cases, and in the end, we need to open up our configuration framework or the possibilities to essentially turn off all that generator stuff and allow the users to produce and inject raw configuration code, raw manifests into Kubernetes, which is sort of the rare configuration cases and corner cases. Stephan discussed that. Let me quickly wrap it up. Let's look at what we achieve. We do have a setup in place that satisfies the users and the platform's requirements, so we can really scale that and have our users use it. It runs reliably for quite a while now. We do have the migration schemas defined how users get their applications into the service mesh. Not as simple as you might think. Sometimes it's problematic to do it in the right sequence. And we do have about 10 to 15% of our applications already using Istio and the service mesh functionality. So next really is to make sure the control plane holds for the full scale, to test the multi-cluster services and find out if that can ease up the configuration efforts. And of course, continuously, we need to improve the automation that we provide. And, well, bottom line, boost the adoption to as close to 100% as we can. So thanks for your attendance. I think we're just barely in time and have a little bit of time for questions because we want to release you on time to the party starting outside.
Thank you very much for the talk. We are right on the schedule, so it's perfectly fine. So we have few questions on Slido. If we can just go through each and any of them, that would be cool.
Okay, did we evaluate Locality versus Istio? Yes, at least on paper. At the time, we made a discussion a couple of years back. Some of the core features that we need, especially expansion and multi-cluster support, had not been in Locality yet. So the original choice was on Istio, and that's where we are sticking right now, but we are keeping an eye on the development of service meshes. We might be able to replace it if something better comes up. Would you recommend to use VPA for Istio? Stephan, maybe.
Yeah, that's definitely a thing which would be possible. Currently, we are not using VPA at all, but HPA, of course, is a fine thing to use for Istio as well. When defining your requests and limits manually, we are quite restrictive on the IstioD so far. So if you give IstioD really a sufficient amount of memory, like if you go to large instances, which are usually larger than the pod would be usually defined, like going into 16 gigs or so for memory, then it will hold a lot more than it does for us currently. So that's something to test for us. VPA would definitely be an option because by that you would learn how much stuff, how much resources does IstioD need, and would auto scale it up if necessary.
All right, next question is, do you still experience performance issues with Istio?
Yeah, maybe I will answer that as well. With the quite restrictive settings we have, sometimes we notice that we go into CPU throttling. But of course, that's just still part of the learning phase, how much resources we do need for a certain phase of the cluster. Usually, this only happens, the throttling problem, when large workloads are rolling redeployed. So if you have a lot of endpoint changes, and this is why we are not so concerned about that.
Right, next one. Why do you make your life hard on your own by choosing Istio? Yeah, obviously because we do absolutely love to do things the most complicated way possible. But honestly, as I said, when we originally did the evaluation and before investing larger amounts of effort, yeah, Istio was obviously the winner of the evaluation. I think it's still one of the service meshes with a very broad range of features. But as I discussed with Rashid before the talk, it's a chimera. It has a good phase and a bad phase. Yeah, that's the way we decided. As far as I understand, a lot of other companies are using Istio as well. From the functionality perspective, it satisfies our needs currently. We have it running stable. But we keep our eyes open, and the nice thing on automation and abstraction is that you can replace single components in a platform without the user suffering from that, because we can translate the abstraction to any kind of actual implementation. Stephan, any additions to that?
No, that's all good.
Okay, what else do we have? Performance, we did have answered that. Does this mean for a cluster failover to fully function, there should be no connections that manage their own TLS, database connections that don't require SSL?
Maybe I can answer that one. The answer is yes and no. So the general suggestion for Istio or for mesh-enabled services is anyway that don't do your TLS on your own, because by that you are removing the option of Istio that it intercepts your traffic and it knows something about your traffic. That's especially true for HTTP traffic. If you use TLS from your workload perspective, you can only see TLS bytes received and transmitted. You don't see the HTTP requests themselves. For the failover case, that does not mean you cannot do failover, because Istio will still be able to redirect your traffic to a different IP address. It will just not know anything about the details inside, only if it runs into timeouts to one workload. By that, the outlier detection will kick in and see, okay, that connection doesn't work anymore. Let's failover to the other IP address.
Okay, we do have one more. How is consensus in the system reached? For example, for outlier detection or when two clusters publish conflicting information?
As far as I know, the outlier detection is completely computed locally in the sidecars. So they just converge to the same information over time. There's no central information regarding that. And that would not scale anyway if you would try to gather a central knowledge about reachability.
Anyway, that setup is a distributed system. And as you probably all know, distributed systems are a beast in general. There's always cases that you easily can construct where clusters or different parts of the distributed system do see different state, and it might be difficult to resolve that. But that's still being researched in universities, so there's no general solution to that. Currently, it seems to satisfy our needs because as well, many of the workloads, if not most, are actually stateless, so they can handle a lot of changes in their environment. The last one, as one of the core principles of Kubernetes is that IPs are ephemeral. Doesn't this raise some issues with the current setup?
Usually it doesn't, because every information from the local cluster, so every moving service IP or pod IP within the local cluster is, of course, directly picked up by Istio and distributed to the Envoy sidecars. The remote stuff would be interesting, and the remote communication goes through gateway IPs, and gateway IPs are not ephemeral Kubernetes internal cluster IPs. So they are rather stable. By now, if I remember correctly, it is possible to not mention IPs, but just use DNS names for that, for your external DNS resolver. So even if your IP would change and that DNS entry would be updated, Istio would know. But as said, that IP is a lot more static than the ephemeral internal Kubernetes stuff. I hope that answered that question.
Yeah,
nice.
Thank you.
Thank you very much for the talk. Thank you very much for answering all the questions. I think it's time for all of us to enjoy the after party. Once again, please have a big round of applause for our speakers.
Thank you very much.